Okay, we're going to talk about exothermic and endothermic reactions. So an exothermic reaction is a reaction where if you've got two reagents that are reacting together, so say we've got hydrochloric acid and magnesium, so here we've got some magnesium in hydrochloric acid. If we were to put our hands around that beaker, we would feel it getting warm. So what's happening is energy is being released from that reaction, and we can feel it as heat. And if we put a thermometer in there, we would see the temperature start to rise. So the temperature would be at 1 point, but we would see it rising. So the temperature would rise because we are releasing heat by having the magnesium react with the hydrochloric acid. So how we would show that in a graphical form is to have a graph where we've got the amount of energy of our reagents and products here. So as you go up this scale, you've got more and more energy, and this is the reaction as it progresses. So it's the reaction progress. We can think of that as time. So as time goes on, how does the energy change? In an exothermic reaction, the reagents, in this case magnesium and hydrochloric acid, have a certain amount of energy associated with them. So there's the energy in the bonds that holds the magnesium together and between the magnesium atoms, and there's the energy in the bonds that holds the hydrochloric acid together. And if we add all of that up, it has a certain amount of energy. So it's going to start, say, about here. So I'm going to say that this is magnesium and hydrochloric acid. So there's a certain amount of energy, and that's starting at this point. Now when this reaction's finished, it's lost energy. So it's lost energy from this. So at the end point, our products have got less energy, and in this reaction magnesium reacts with hydrochloric acid. This should be 2 hydrochloric acids. It gives hydrogen and magnesium chloride, so our products are hydrogen and magnesium chloride. But the energy that's in the bonds that hold hydrogen together and the energy that's in the bonds that holds magnesium chloride together, when you total that up, that's less than it had at the beginning. So here these are our products, which are hydrogen and magnesium chloride. So there's less energy there. So what we've done, we've actually lost energy. So that's an energy release. Energy release. Okay, and this difference is called the enthalpy change. Okay, so that's got the name enthalpy. Enthalpy is just a posh word for energy, so enthalpy change. And as chemists, we like to do a little bit of a shortcut. So enthalpy change is a long word to keep writing. So change, we represent change with a symbol. It's a delta symbol. So change is a delta symbol. And enthalpy we represent as the letter H. So an enthalpy change we call a delta H. So delta H and enthalpy change are the same thing. Now because we're losing heat and we're giving heat out, then we say that delta H is negative. So it gives out H, so it's negative, so it has a minus sign attached to it. So delta H is negative, and there'll be a value that we can put on that. It might be 50 kilojoules or 100 kilojoules per mole, or it could be 200 kilojoules per mole, but that would be a negative value. Negative means to lose, so we're losing heat to the surroundings, so we feel something getting warm. Now, the other thing is the magnesium atoms have to be broken apart, and the hydrogen and chlorine atoms have to be broken apart. So we have to put some energy in to begin with. And once we've broken them apart, so at this top here, we've broken them apart, they can reorientate themselves. So the magnesium atoms can then go with the chlorine atoms, and the hydrogen atoms can come together. So then it comes down like this. So what we've got here, this is the energy that we need to break those bonds, and we call that the activation energy. Activation energy. And that's the minimum energy required to start the reaction. But it's equal to the bonds breaking. Okay, so we've got an activation energy, and we've got an enthalpy change. So that's the energy change from the reactants to the products, and that enthalpy change is negative. So if we were to put some values on this, if this energy here was, say, I don't know, let's give it a value of 100 on this scale, so that would be 100, and say down here this energy value was 50, the difference would be the energy of the products, which is 50, take away the energy, so that's the energy you ended up with, take away the energy you started with, which goes to minus 50. So it's 50 take away 100, which is why it's negative. I will talk about that in another lesson, but this is why it's negative. Okay, so let me look at an endothermic reaction. So an endothermic reaction is something that takes in heat. So endothermic, it requires heat, it requires energy for the reaction to go, or the change of state to go. So it requires energy to react. If we think of something like a solid, so here's my solid particles, and we put them into water. Here we go, put them into water. Those solid particles are going to split apart, but you can see we've got attractive bonds here. So if this is like sodium chloride, which is ionic, you've got electrostatic forces of attraction, so you're attracting, so you've got some energy that you need to break, so you need more energy, and you need to break those bonds. So what happens? The solid takes in energy from the water to break those bonds, and what we see is that the temperature of the water, if it was up here, the temperature of the water goes down because the energy has been taken out of the water to break those bonds. What does that look like as an enthalpy diagram? So this is our energy here, and this is the progress of our reaction. So we have an energy that's associated with the solid. So as I say, this might be sodium chloride, or it could be ammonium nitrate, or it could be potassium chloride. Let's say it's potassium chloride. So potassium chloride, we're going to add it to water, so potassium chloride and water, and what happens is it dissolves. And as it dissolves, the temperature goes down. So there's a certain amount of energy associated with the potassium and chlorine bonds. So that's potassium chloride here. And when it dissolves, it splits into its ions. So it splits into potassium ions and chloride ions, and they're separate. Okay, I'm going to put aqueous here so that we show that they're dissolved. And the potassium chloride is a solid, so that's a solid. Now, we're having to put energy in to break these bonds, so actually the final particles have more energy now than these did. So potassium and chlorine ions, the ions have more energy, so it's taken a lot more energy to go from here to here, so we're putting energy in. So this change here is the enthalpy change, and remember, change is delta, that's what the symbol means, and enthalpy is H, and we're having to put energy in, so we say that the delta H is positive. Okay, so if this had a value of, say, 20 and this had a value of 80 for energy, it's the energy of the products take away the energy of the reactants, so 80 take away 20 is plus 60, so that's why this enthalpy is positive. Now, in order to go from potassium chloride to potassium and chloride ions, we've had to break the bonds. So this, from where the reactant is to the top of this curve, is the activation energy. Activation energy. So that's the minimum energy required for the reaction to occur. It's like climbing up some ladders to go down a slide. You've got to climb up a lot of ladders, but you don't come down very far. So you're gaining lots, if you think about it as potential energy, you're gaining lots of potential energy and you only get a little bit of kinetic energy back. Whereas with this one, you're starting, say you're on top of a hill, you only need to climb up a little bit, so you're only putting in a bit of energy, a bit of potential energy, but actually you slide a long way down, you're gaining quite a lot of kinetic energy. It's just an analogy, that. So this is our endothermic reaction. So we don't have a lot of energy to begin with. We put in a lot of energy to be able to get the reaction to start, and we only get a little bit back. So this is the enthalpy change is positive. And so this is what our reaction profile looks like. We read them from left to right. So we read them from reactants to products, which is exactly like reading a chemical reaction, because our chemical reaction goes from left to right. It goes from reactants to products. So that's all we're doing. We're reading it from reactants to products. We're looking at the energy of the reactants and we're looking at the energy of the products. So I hope that's going to make it a little bit easier for you.